Welcome to RT Basel. Thank you for coming, and it's a pleasure to have Camille Maumet with us today. And she has background in computer science, and she's currently working as a research scientist at INRIA of the University of Rennes, and also at IRISA, also in France. And she's doing studies in neuroimaging reproducibility. And in her current research, she focuses on the variability of analytical pipelines and its impact on our ability to reuse and use brain imaging datasets. And she's also an open science advocate and is participating actively in national and international communities, including BITS, the Brain Imaging Data Structure, BrainHack, and the French Committee for Open Science. And today she will talk to us about improving computational reproducibility. So she will tell us how to share our research code. So please, Camille, the stage is yours.
Thank you so much. So thanks very much for the introduction, and thanks for having me today. I'm really delighted to be doing this talk. So let me share my slides first. Today I'm going to focus on one specific point, one specific scientific artifact that we might want to share, which is research code. And by way of an introduction, I'll just start with this. So here I've titled this an MRI study, but of course this could be true of any instrument you're working with in your research. And so basically here we have a schematic overview of how a typical study might look like. So we're going to do an acquisition, get a lot of data, then these data are going to be pre-processed. We get derived data, and then we're going to apply a statistical analysis at the end and get our final results. But when we think about, and this is, so maybe we're happy with what we found, this is our research, and we have this finding we're really excited about. But then if we think about how we're going to share that with the community, of course, this is no surprise if I tell you that we're going to write a paper. And then basically the paper is the only thing that is going to remain of that whole nice study, because that's what we're going to give to the community. And now, if we put ourselves at the other end of the spectrum, we're not the person writing the paper, but we are the person reading the paper. And probably you've been in that position when you try and understand what has been done in a study, because that's typically how we build research, right? We build on each other's findings so that we can expand the area of our knowledge. And then basically you try and reproduce a study, and I cannot reproduce the published results. And when this happened, basically a lot of questions appear in front of us. So maybe I couldn't reproduce because, well, in the paper, it wasn't stated which exact version of the software was used. Or maybe the type of registration algorithm was defined in broad term, but I don't know which one specifically was used. Or sometimes there are even parameters that we don't typically describe in research papers, but that we still know have quite an impact. So that, for instance, the way the brain mask was computed may be one of those. Then more generally, as we try and reproduce, we might ask ourselves, okay, did I just not understand the method correctly, and that's why I just can't get the same results? Or maybe that's because I have a different data set, and basically my data set is leading to different results. Or maybe my different computing resources, or even something else I can't even think about. And of course, this situation is not great, and we're a bit at a loss. And this is telling us maybe we should share a bit more than research papers. And of course, you've probably heard a lot of that in that seminar series. So now our research finding, which we were so excited and was so bright, is not so bright anymore because, well, for someone else, it's not so clear how we got there. And so the idea here is that throughout the whole analysis, we might want to try and share more research artifacts. So before I dig in the code, because that's why we are here today, the first research artifact we've been discussing a lot when we talked about open science is the research paper itself. And there are a number of initiatives that makes it possible to make research papers available to more people. These include preprints or diamond open access. And these are all important and part of open science, although I'm not going to cover those, but happy to chat about this later if that's of interest. Another research artifact that people have been discussing a lot in terms of sharing is the input data. This is even more important in fields of medicine or biomedical research that involve human participants, because basically each time we perform a data set, we get a data set. First, there are, of course, costs, because you might use an instrument that is very costful, such as an NMR scanner, and of course any amount of time used for acquisition on that machine corresponds to a number of money. But in addition to that, you're also using the time of the participants who are willing to take part in this analysis, and also the time of the expert physician and technician around the machine who makes the acquisition possible. So our input data set are usually very, very valuable, and that's why a lot of effort has been put into trying and understand how we can share these so that it can be reused by the community. And this has led to the development of the so-called FAIR principles, which we've heard a lot about. So FAIR stands for findable, accessible, interoperable, and reusable. And those are basically best practices that we can use when we want to open data. Because if you've tried to reuse data, you've probably been in that situation where someone, so it could be a colleague and from another lab abroad, or it could be a colleague from your own lab, or it could be yourself, your past self 6 months from now, that gives you a folder and tells you all my data is in there. And then you look in there and it's really hard to make sense of it, and you're not even sure you have the latest version of the file, and so on and so forth. And here the FAIR principles are helping us to make sure that we use the appropriate steps so that the data we share can be meaningful. In the same way, we've been working on open data. We might want to be able to share what's in this part in the middle. So first we have derived data, and those we could share just like we did for the input data. So I'm not going to get into those details, even though there are also consideration because those data sets are getting bigger and bigger. But if we think about this more specifically, basically in that step, a lot of the valuable information is about what are the specific processing we've done on the data in order to get our final results. And typically this is available in the form of code. And the question is then, okay, how can we open up these codes? Are there best practices we can follow in order to make sure that this code can be meaningful for the other people on the other side trying to reproduce or just understand what we've done in our study? Just like we've had the FAIR principles for open data. And so we'll dig a little bit more into this. And one interesting point here is that for open data, if you work with data from human participants, sometimes it's not so easy to share the data if you think about it too late in your analysis. Let's say you've done all your analysis, your paper is ready, and then you want to share the data. If you haven't thought from the beginning that you needed to get consent from your participants, then this is going to be very complicated. The good news with code is that typically the code is developed within the team that works on the project, so there are less difficult consideration in terms of whether we can share code or not. Of course, I'm not saying there are no considerations, but just it's probably a little bit easier. And this is also, in addition to data, a research artifact that I believe has a really big value, but here for the scientific community to understand what was done in the paper. And so here we go. So I've been touching upon reproducible research a little bit in the first slides. Before we continue, I just want to define two terms. So I know definitions in reproducibility are confusing because sometimes we use them one way and sometimes we use them the exact opposite way. So in the following, here are the two terms that I'm going to use. So On one end, we have computational reproducibility. So this is the idea that we try to reproduce exactly the same results using the same data, the same code, the same environment. We stay in the very same context. This is the type of reproducibility I hear most about when I talk with computer scientists. And then at the other end of the spectrum, we have reproducibility. And here it's the idea that we want to make sure that our scientific findings is still correct if we change a little bit the context. So maybe we're going to work on a data set that is not exactly the same. Maybe acquisitions for my studies were all done in Rennes in France, and I want to test the data set on data that was acquired in Basel, and I want to make sure that my finding stays. That's true for the data, that's true for the method as well. And in the following, we're going to focus on computational reproducibility. So basically how we can share the different research artifacts and put them together to reobtain the original results. But I always like to say that this is like a first steps toward replicability, because quite often when you want to understand which parameters, being either the data or the method or a mix of both, has an impact on your scientific findings, you retrieve yourself into trying and reproducing exactly what was done before you can change and add levels of variations. And so in the context of computational reproducibility, we're going to think about what can be best practices to share code. And the first practice, which is probably the one that comes really quickly to our mind, is to have the code open source. So basically, open source is about two things. First is about having an access that is available to everyone. So here the suggestion is to put the code in a public forge, because that's both a way to provide access to everyone, but also to keep the various versions, because that's what an aspect that is very specific about code is that it changes a lot through time, probably much more than data is changing, and using an open source license. So that's the first step. It's going to bring transparency on what was done. So for instance, for me, as a neuroimager, specialized in task fMRI, if someone, in addition to their paper, shares a script of task fMRI, I can go and read it and get a deep down understanding of what was really applied on the data. So that's very useful for like experts who wants to review the code. But this by itself is not enough to guarantee that the code will be available through time. And this is very important to me because it's often overlooked. Basically, if we only use, let's say, GitHub, because that's a very popular public forge, if we only put GitHub links in scientific papers, we have no guarantee that those links will still link to our code in the future. Just like when we share data, we use data repositories. When we share code, we need to use repositories that have been built with preservation, with long-term preservation in mind. And for this, so we have first Denodo, that has a nice integration with GitHub and has been out for quite some time now. I'd say, well, I don't know how many years, but quite some time. And then we have the Software Heritage Archive. So this is more recent. What's nice about Software Heritage is that it's an archive that is dedicated to code. So basically their goal is to build a big graph of all the open source code in the world. And again, they have nice integration with public forges, so that's just a few clicks. That's just a few clicks, but those clicks are very important because they will guarantee that your code that is now visible on GitHub or GitLab or whatever will stay available in the long term. Then there is a third step. But we'll see later that this one is optional. So the idea is that for code to be understandable and reusable by other people, we need to add some level of documentations. Of course, we could go very, very far in terms of documentation. So here I've included a few hints that are good first steps, basically, to add documentation to a code. The first one is to have an explicit list of authors And authors can be people who wrote the code, but also people who wrote the documentation, people who had the idea about the software, and so on and so forth. So we need to be careful about contribution not being just commits in a Git repository, because there is much more than that in software development. And then there are a number of software development best practices that help a lot, including being careful about the namings, being the namings of the functions, the files, the variables, commenting, of course, always, and then having examples. I put here at the bottom two different documents. So the one on the left is basically a file hierarchy. So that's one thing that is quite nice when you get a repository that is associated with a paper, is that people who created the repository guide you into finding the interesting information. So what we've been trying to do in my lab and in others is to try and have two things. First is to reuse always the same file hierarchy. So basically you have a folder in which you put the code, you have a folder in which you put the results, you have a folder in which you put the code to reproduce the figures, and so on and so forth, trying to be explicit about what's in there. And then we have a README that goes with it and say, okay, you would like to reproduce figure 1. You should look into that file and then run this and this, and you'll get all the steps that leads you to figure 1. And this sounds super simple, but when you're getting into a repository that you don't know, or your own repository from yourself in the past, that's super valuable. Then there is one thing we have been not touching upon yet, is the idea, and I'll get more into details about this just after, is the idea that typically our code doesn't work in isolation. Our code is based on a code base itself. It's based on dependency, operating system, and so on. And so as a first step, and we'll see we can, of course, go further than that, listing dependencies so that people know what they have to install in order to try and reuse your code is a best practice. So that's kind of minimal documentation we can add on top of making the software open source and the code available in the long run. So now you might say, okay, we found a way to share our source code. We've listed our dependencies. Are we all set now? Can we say that if the data is shared as well, of course, our results are computationally reproducible. So again, this is the idea that we want to get the very same outputs from the same data and the same code. Well, it turns out actually not really. So before I get any further, I want to say, actually, that's okay. And in open science, we need to be very careful, because often we end up by saying, you should do this and this and this and this, and it ends up like this huge mountain that we have to climb. The idea of sharing your code, I think, first, to me, is to be transparent about what was done in your paper. And if you stop here and you only make the code open source and archived, and if you want to add a little bit of documentation, this is great already. But now we can discuss a little bit what can we do if we want to go one step further. So why are the results not computationally reproducible yet? First, because beyond the source code you've been sharing, there is an environment, so I've touched upon that in the previous slides, including operating system libraries that are required for re-execution. And the only way and basically you have to give a description of all these if you want to be able to get closer to computational reproducibility. And in fact, I believe this is still an open question. So there are a number of computer scientists that work on that specific problem. So can we reuse a code and make sure that we ship all the dependencies with it and get the same results? And there was this project a few years back in 2020, 5 years ago, where basically they've put out this challenge, trying to see if people would dare reuse their code so reusing your own code from 10 years back. And the only fact that we still have this kind of challenge is telling us that this is not a solved problem. But if we want to go further, there are ways to build computational environments, could be based on Docker, or even better, geeks or nicks. So basically, geeks or nicks are software solution that makes it possible for you to specify specifically all the version of your dependencies, but then you go down the trees and the version of the dependencies of your dependencies up to deep down. And this way you have specifically defined the base on which your software is running. Okay, so trying to recap a little bit. So how can we open up code? So first, please note on the left, what's mandatory basically for, I would say, as best practice is only what's here at the top. So having a code that is open source and that is archived. And this brings transparency, which is so important already. So open source license in a public forge and then archive using a repository for long-term preservation. And if we want to go one step further, we can add up some documentation for reusability, including crediting authors. And we've seen a number of best practices, including using meaningful names and listing dependencies, using a README, having a structure that is very clear about where which files are used to reproduce which figure, and so on. And then optional, if we really care about the fact that our code must be executable, then it's useful to have a computational environment that we share with the community so that people can put our code on top of the pile of software that are important for it to rerun. Okay, so we've been discussing so far mainly computational reproducibility. I've mentioned replicability briefly. But when we talk about software, so far I've been discussing mainly about the code you write for your research paper, but there is also the question of software. Sometimes you write, so what I mean by software is a piece of code that you write and want to share for others to reuse and maybe apply on their data and so on. So basically here we define reusability as the ability to reuse a research artifact for other purposes. So we talk about secondary use. We talked about secondary use a lot for shared data, but similarly for shared code, you might want to have a piece of code that is reused by other people. And so how do we do that for software? So basically we're going to build on the basis that we've covered already. So when we have a code that is open source, how can we bring people to collaborate? So open source really define who can access and use the software because the license gives the right to use the software. When we think about collaboration at this very beginning, there are two things that I think would be are important to add and close to my heart. The first is having a code of conduct, making sure that people who are going to contribute around your codes do it in ways that you think is relevant and is welcoming. And then set expectations. Maybe that piece of software you wrote is public, but is not expecting any contributions. And that's fine. You can write it as such and say, okay, I'm not expecting contributions. I don't have time anymore. This was a piece of software that I use maybe for my postdoc. I want it to stay there because I want transparency, but I'm not maintaining it. And that's totally fine. But then setting expectations by saying it explicitly with your code, I think, is a very good way to basically start the realm of collaboration, even if it's to say, okay, I don't want people to send pull requests because I won't have the time to deal with it. Okay, so that's the first step, but let's put ourselves not in the context where we don't want to collaborate, but in the context where we want to collaborate. Next step after open source is to think about open development. So open development is no longer about who can access and use the software, but in addition, we think about who can contribute to that software. So this includes accepting external contributions into your code base. This might be in the form of pull request on GitHub or whatever. And also be transparent in terms of development choices. Sometimes writing an issue saying there is this big feature change that is going to happen is very useful. Having a project board, giving some idea of what's going to happen is also helpful for people to contribute. And then the last step is to try and think about who can decide for future direction. So this is what we've done here, open governance. So basically, you can decide who can use and access your software, who can contribute, but then here it's about who can decide for the future. So this is having a transparent way on making decision. Basically, are you, and maybe it's someone in leadership who makes the decision, but then being transparent about this, I think is already a huge step. And then creating pathways for people to join the leadership is another important one. Of course, again, all of this doesn't have to happen at once. It's a process, and we can start at the very beginning of the ladder and then grow as we go through this path. Okay, so all of the things I've discussed today is available in a document. So there is a link here at the bottom, which is called the Code Roadmap. So code stands for collaborative, open, documented, and executable. It's basically a series of steps. So you're going to retrieve the steps that I described earlier that are mandatory, recommended, or strongly recommended, and then optional, with the idea that collaborate is fully optional. Executable, you have some recommendation to basically list the dependencies. So you retrieve all the things that I had on my slides. And this is available in a full preprint that you can read and then to get more into the details of how you can do all of this. And so now we've seen how to share the publications. We've seen briefly, we've discussed how open data have been discussed a lot. And now we have a way to more specifically share our codes. So basically using a public forge to store it and then archiving into an archive that is dedicated for code, or an archive that accepts code. And basically this gives us this full outline of how from our original study we can share much more research artifacts than just a scientific paper. And I think this is about it for me today. I would be very happy to answer any questions or to continue the discussion. Thank you very much.